Hello, and welcome to the tutorial on how to use and interpret Vermont's next generation lake assessments. My name is Kelly Merrill, and I'm an aquatic ecologist with the Vermont Lakes and Ponds Management and Protection Program, which is part of the Watershed Management Division in the Vermont Department of Environmental Conservation. The Watershed Management Division is responsible for monitoring the status and trends of the state's waters. The Vermont Next Generation Lake Assessment is a summary of the status of a lake from a one-time comprehensive sampling visit to an inland lake. During this visit, sampling occurs at what is thought to be the location on a lake or pond with the deepest depth, which we call the index site. We also sample all the tributaries draining into the lake and make observations at where the inlets meet the lake. Finally, we conduct a physical habitat assessment of the lake, visiting 10 randomly selected sites around the lakeshore to assess. The U.S. Clean Water Act's goal is to maintain and restore the chemical, physical, and biological integrity of the nation's waters. The Vermont Next Generation Lake Assessment measures chemical, physical, and biological parameters with the intent of determining if the goal of the Clean Water Act is being met for a given lake. Why Next Generation? The Lakes and Ponds Management and Protection Program has been conducting sampling during the summer index period since the 1980s. However, while some chemical, physical, and biological samples were taken during those visits, many of the observations made were very qualitative. The Next Generation Lake Assessment was developed in 2010 using a mix of sampling approaches from the Vermont DEC's qualitative assessments, the U.S. National Lakes Assessment, and from the Vermont DEC Littoral Habitat Assessment approach. Not all inland lakes have had a Next Generation Lake Assessment conducted on them. And moving forward, Vermont DEC is prioritizing sampling lakes where our long-term spring turnover monitoring or summer lay monitoring data suggests water quality conditions are deteriorating. These assessments are designed to help lake watershed action plans determine if more targeted data collection is necessary and where to focus restoration and protection efforts. These assessments are also intended to help folks better understand the existing conditions of a particular lake. But before we get started, I'd like to acknowledge my colleague, Dr. Leslie Matthews, who created these interactive reports. Without her determination, ingenuity, and creative ways to display and share our data, the stories this data can tell us about our lakes and ponds would be stuck hidden in databases and on paper inaccessible to the people most able to maintain and restore our state's lakes. You can access these Next Generation Lake Assessment interactive reports from two different websites. From the Next Generation Lake Assessment landing page, shown here at this website at the top of the page, or just Google Vermont Next Generation Lake Assessment. You can also access the reports from the Vermont Lake Scorecard webpage, which has a link to a report viewer page that gives you additional information on a particular lake as well. The links for the Next Generation Lake Assessment is found in the last column in the table here shown at the right. So I'm going to use Lake Willoughby's Next Generation Lake Assessment as an example to show you how to interact and interpret these assessments for any of the lakes. Depending on your internet speed, it may take a minute or two to open up, but once you open up, you'll see a satellite view of the lake with the outline of the lake watershed around it. This watershed includes the entire drainage area for the lake, including any lakes which drain into the lake of interest. The watershed outline color denotes the watershed disturbance score. The watershed disturbance score is derived from a landscape development intensity index developed by Brown and Vivas in 2005. The LDI is a measure of human-induced alterations to the biological, chemical, and physical processes of a watershed's lands that impact the receiving water. In this case, a lake. Watershed delineations and corresponding land use intensity data used to calculate the LDI for the 2017 Vermont Inland Lake Scorecard came from the Nature Conservancy's Northeast Lake Classification System. Coefficients used in the LDI come from the Ohio EPA Division of Surface Water Wetland Ecology Group and are shown in Table 5 below. Land uses within each Vermont lake watershed were assigned in land class from Table 5. The Landscape Development Index was calculated as an area-weighted average as follows, where LDI total equals the Landscape Development Index ranking for the entire watershed. Percent LUI equals the percent of the total area of influence in land class 1, and where LDI equals the landscape development intensity coefficient for land use I. Thresholds for scoring Vermont lake watersheds were determined using the best professional judgment of Vermont Lakes and Ponds program scientists and are shown in the table below 6. The final watershed disturbance score is denoted by the color of the watershed outline, with blue being minimally disturbed, yellow being moderately disturbed, and red being highly disturbed. So we see that Willoughby's watershed ranks as moderately disturbed using the Landscape Development Index and Lake Watershed Disturbance Score. Note that the map is interactive. You can zoom in and out by using the plus or minus signs in the top left-hand corner and zoom back out to full extent by using the icon under the plus and minus sign. The next thing I'd like to draw your attention to is the lake condition scores at the right-hand side of the landing page, where blue indicates good, yellow indicates fair, and red indicates poor condition. The thresholds for these scores come from the U.S. Environmental Protection Agency's 2007 National Lakes Assessment and allows us to compare the condition of a Vermont lake to the condition of lakes in the nation and northern Appalachian ecoregion, which is shown in blue in the northeast part of the U.S. on the map of ecoregion shown here. If you're interested in learning more about the thresholds used, you can refer to the Gauging the Health of Vermont Lakes report, where you can see the breakdown in condition for the nation, each ecoregion, and Vermont for each of the condition parameters in the summary page of the Next Generation Lake Assessment. So this page serves as a summary, a report card of sorts for the lake. But we'll go into details about each of those parameters when we start exploring some of the tabs at the top. This page is intended to give an overview of the overall condition of the lake. Clearly, Lake Willoughby rates good across the board, with the one exception being its score of fair for lakeshore disturbance, which we'll go into in more detail later. So the take-home message from this page is that Lake Willoughby is in good condition overall, but has a moderately disturbed watershed, and its lakeshore is in fair condition for lakeshore disturbance. If planning a lake watershed action plan, this information might help prompt a closer look for potential sources of pollution to the lake near tributaries draining into the lake and the need to promote lake-wise practices at lakeshore properties. The next thing I'd like to draw your attention to is the menu items along the top. Here you see the date the survey was conducted, and then you see tabs for water quality, habitat, inlets, protection classification, and data. So let's click on the water quality tab now. Now the water quality tab summarizes the readings taken at the index site, part of the lake with the deepest known hole. Now there is a lot to unpack here, so let's start by zooming in to the top. You see there are 3 hyperlinks across the top. One that it will allow you to view the profiles taken at the deep hole during visits to the lake at spring turnover as part of the spring monitoring program. Clicking on this sends you out of the Next Generation Lake Assessment Report to see data collected on the lake during spring turnover for a variety of parameters over a number of years. You see the parameters across the top. Depth is on the y-axis with the surface of the lake at the top of the graph and the bottom of the lake at the bottom of the graph. If you scroll down on the right, you'll see for Willoughby we have profiles going back to 1978. We see another hyperlink that is for viewing the summer profiles at the lake that have been collected over time. These are useful to look back in time and see how the profile taken during the August 30th, 2017 visit to Lake Willoughby compares. Here we see summer profiles for Lake Willoughby going back to 1972 for comparison. In this case, scrolling down brings you forward in time to our most recent profile, which was from the QC visit conducted as part of the lake monitoring program in 2021. If we go back to the Next Generation Lake Assessment Report for Lake Willoughby's water quality page, we see another hyperlink that is for viewing the lake scorecard for the lake. This is the Vermont Lake Scorecard for Lake Willoughby, which is a summary of the status and trends for the lake, and there's a whole other recording on how to interpret this data. But let's go back to the Next Generation Lake Assessment Report. Here you were told that when using the report, if you want to know the value for a particular point on a graph, all you have to do is hover your mouse over the point to see the values. Now we can look at another parameter measured during this visit, Secchi transparency, which is a measure of water clarity, and if you hover your mouse over the plus sign in the middle of the circle, you'll see 6.1 meters pops up. That denotes the depth the Secchi disk disappeared from sight during this August 30th visit to Willoughby in 2017. To see how this 6.1 meter reading compares to readings taken on the lake by the summer lake monitor over this time period, you can go back to the Vermont Lake Scorecard. And we see this visit's reading is not uncommon for this lake. But there are times when the reading is much deeper and clearer, and there are times when the reading is much shallower and less clear. During the sampling visit, a multi-parameter SON is sent down through the water column. Here on the left, we see Jess Davison, the inland lake scientist intern in 2022, getting ready to deploy the SON for sampling on another lake. In the graph, we see the resultant profile for Lake Willoughby with depth on the y-axis and the surface of the lake at the top and the bottom of the lake at the bottom of the graph. Depth is in meters, and we typically take readings at 0.2 meters below the surface and then at 1 meter intervals until we are approximately 1 meter above the bottom. In blue, you see the profile for temperature. Now, since it's summer, the temperature at the surface of the lake is warmer than in the bottom waters. We see it's about 20 degrees Celsius until about 12 meters deep, where we see a sharp decline in temperature at what is called the thermocline. The thermocline is the part of the water column where we see the biggest change in temperature. From about 30 meters depth, the temperature is pretty uniform, going to the bottom at around 5 or 6 degrees, which again, if you hover your mouse over the points, you'll be able to see the actual readings. Next, we can look at the DO, or dissolved oxygen profile, that is shown in black in this graph. Here we see that dissolved oxygen is running at about 8 milligrams per liter above the thermocline near the surface, and then it's a little higher below the thermocline. This is because colder water can hold more oxygen. And in some lakes, you see that as you get closer to the bottom, the dissolved oxygen levels decrease because algae from the water column settle to the bottom and die and are consumed by bacteria which consume oxygen. But what's interesting about Lake Willoughby is that it has plenty of oxygen all the way down to the bottom in August, at the end of August, when lakes are typically going to be more productive. But because this is an oligotrophic lake and there's not a lot of algae in the water column settling down, there is a high amount of oxygen throughout the water column. Now let's look at the chlorophyll A profile. Chlorophyll allows plants, including algae, to photosynthesize, which means using sunlight to convert simple molecules into organic compounds. Chlorophyll A is the predominant type of chlorophyll found in green plants and algae, and there are two different ways that chlorophyll A is collected during our visit. One is using the sonde shown here with our intern Jess on the left, and the other is to bring a sample from an integrated sample taken from the top 2 meters of the water column and bring it back to the lab to be extracted. The absolute values from the sonde readings are not to be used as equivalent values for the extracted chlorophyll A. The utility of the sonde readings is to see how the readings change with depth in the water column. So for our Willoughby visit, we see that there is very little chlorophyll A at the surface and from 40 meters to the bottom. However, at about 20 meters depth, there is a peak in the chlorophyll A reading, suggesting that is the sweet spot for the algae that live in the water column in Lake Willoughby during our visit. With the right balance of light penetration and nutrient availability for photosynthesis. Seeing a chlorophyll maximum like this is common in lakes in the summer, and we've begun taking extracted chlorophyll A samples at this depth and phytoplankton samples for Dr. Mindy Morales at the University of Vermont from this location in the water column as well. Jess is shown with the phytoplankton net used to sample here on the right. This collaboration with Dr. Morales will expand our understanding of what species of phytoplankton are living in Vermont's lakes in the summer at this sweet spot. So now let's move on to the panel for total phosphorus. Here on the right, you see my colleague, Dr. Leslie Matthews, getting ready to deploy a Chemer sampler that allows us to take water samples from discrete depths in the water column. Using the Chemer, she is going to take samples from the middle of the epilimnion, which we sample at half the thermocline depth. She's also going to take samples from the location halfway down from the thermocline in the hypolimnion. And finally, she'll take a sample at 1 meter above the bottom. Although during this visit, our Chemer line wasn't long enough to get 1 meter above the bottom in Lake Willoughby, so we took that sample from as deep as we could reach. Since Willoughby is our deepest inland lake, we don't typically run into this problem. At the top of the graph, you see a little red line near the 5 mark. That shows the sample reading from the 2 meter integrated sampler, which is shown on the left. So the samples taken with the integrated sampler and the Chemer were taken back to the Vermont Agricultural and Environmental Laboratory in Randolph, Vermont, to be processed for total phosphorus. Now, phosphorus is considered the primary limiting nutrient in Vermont's inland lakes, which means that photosynthesis by algae and plants increases with increasing phosphorus. There are cases where nitrogen can be the limiting nutrient or where both phosphorus and nitrogen can be co-limiting. Again, the y-axis denotes the depth and the x-axis across the top denotes the concentration of total phosphorus in micrograms per liter. We see in our graph that all the total phosphorus values were below 6 micrograms per liter this day that we sample. These are very low total phosphorus readings and are consistent with what one would find in an oligotrophic or low nutrient lake like Willoughby. So next we are going to scroll down to the next row of graphs in the next generation lake assessment and look at total nitrogen. Total nitrogen samples are taken the same way that the total phosphorus samples were, at the surface with the 2 meter integrated sampler, at the middle of the epilimnion, the middle of the hypolimnion, and 1 meter above the bottom. Here we see that, like total phosphorus, our total nitrogen values expressed in milligrams per liter are low as well, and they seem to be similar no matter where in the water column the samples were taken. Now let's move on to the next graph, which shows the conductivity profile. The Ohio Watershed Network has a nice description of specific conductivity, which I'm going to use. Specific conductance, also called conductivity, is a measure of the ability of water to conduct an electrical current. Specific conductance is an important water quality measurement because it gives you a good idea of the amount of dissolved material in the water. High conductivity indicates high dissolved solids concentrations, and that can be an indication of poor water quality. Here, when we hover our cursor over the data points, we see the conductivity is ranging between 95 and 99 microsiemens per centimeter. These are relatively low readings. For example, in some polluted streams in the state, we can have conductivity levels an order of magnitude higher than this. On the other hand, really low conductivities, those below 25 microsiemens per centimeter, are typical of acid-impaired lakes with really low dissolved solids. Willoughby is at what could be considered a healthy conductivity. Now, when looking at conductivity profiles like this, some lakes that go anoxic or have little dissolved oxygen at the bottom will also show higher conductivity readings near the bottom than in the rest of the water column profile. When we see this, it is an indication that some dissolved solids are being released into the water column from the sediments. We see no evidence of this at Lake Willoughby at this visit, and given the oligotrophic nature of the lake and that there's plenty of oxygen in the bottom waters, we would not expect to see that. The next graph we are going to look at is the one for total chloride. Now, while chloride can be naturally occurring in some places, when we see it in Vermont, it is likely from road salt or possibly from the use of water softeners in domestic water systems. The minimum detection limit for total chloride at the Vermont Agricultural and Environmental Laboratory, where we run our samples, is 2 milligrams per liter. And there are lakes in Vermont that have no sources of chloride pollution, where the readings on those lakes are at that 2 milligrams per liter detection limit. However, Willoughby is not one of those. While the concentrations measured are still very low and close to the detection limit, we did pick up some indication that chloride is making its way into the lake from human sources, likely a combination of both road salt and possibly the use of water softeners by lakeshore camp owners. We take samples for total chloride from the 2-meter integrated sampler at the surface and from 1 meter above the bottom, or as deep as we can get here in Willoughby. The reason for taking readings at both the surface and the bottom is because in some lakes in the Adirondacks, which have received heavy loading of road salt, the chloride accumulates in high concentrations at the bottom, creating a density gradient in the water column which prevents the lake from ever mixing the surface waters with the bottom waters, even under heavy wind events or at spring and fall turnover. Thankfully, we have yet to find a deeper lake in Vermont where the road salt loading is that intense. If you were to hover your cursor over the integrated sampler reading at the surface, you'd find that the reading was 3.44 milligrams per liter, and the reading from deep in the lake was 3.19 milligrams per liter. These concentrations are not alarming, but they do indicate that some chloride pollution is making its way into the lake. Currently, there is no known way to remove chloride contamination from a lake, so efforts to reduce the runoff of road salt and de-icers used by camp owners and to keep domestic water that's treated with water softeners from reaching the lake are the best way to manage for this pollutant and protect the lake into the future. Interestingly, looking at the total chloride readings taken during spring turnover since 2006, we see total chloride readings have significantly decreasing trend. Willoughby and Seymour are the only 2 lakes in the state with significantly decreasing total chloride trends. And it would be interesting to know if that is a result of a concerted effort to reduce the application of road salt, or just that it coincided with years where less road salt was needed to keep the roads safe. Now we're going to scroll down to the second to last row of graphs in the water quality tab for the index site. And here we see the pH profile for the lake. A pH of 7 is considered circumneutral, and we see that above the thermocline, the pH during our August 30th visit to the Lake Willoughby in 2017 was running at about 8 pH units. Then it drops down to 7 pH units from 20 meters depth to the bottom. In acid-impaired waters, the pH can drop to levels as low as 5 pH units in Vermont, which interestingly is close to the same pH as a bottle of Coca-Cola. In some lakes, we see really high pH readings when a lake is having an algal bloom or there are a lot of plant growth. And the Vermont Water Quality Standards state that pH values shall be maintained within the range of 6.5 and 8.5. So all of Willoughby's values fall well within that range. Next, we can move over to the graph that has both calcium and magnesium readings from the integrated sampler on it. According to the International Institute for Sustainable Development's Experimental Lakes Area website, calcium is a critical element in freshwater systems for many levels of the food web to stay healthy, and reduced levels may have negative impacts on the health of our lakes. Our original purpose for collecting total calcium samples was to understand what lakes might be more susceptible to invasion by the invasive zebra mussel or quagga mussel, as these two invasive mussel species from Eastern Europe have calcium concentration requirements of at least 12 milligrams per liter, and they are highly unlikely to invade lakes where the concentrations are below that. The total calcium level measured at the surface in Lake Willoughby during our visit was 15 milligrams per liter, which is above the 12 milligram per liter requirement for zebra mussels and quagga mussels, so Willoughby could potentially support those species if they are introduced to the lake. And looking at the other total calcium data we have from Willoughby going back to 1997, we see that during the spring, levels of total calcium are consistently above the 12 milligram per liter minimum and below 20 milligrams per liter. The next graph in this row shows the values of iron, manganese, and aluminum. These readings are most useful when they are taken both at the surface and the bottom of the lake. And unfortunately, we don't have bottom samples from this visit, but if we did, we'd be most interested in seeing if the values at the bottom were very different from those at the surface. And along with the conductivity readings and total phosphorus readings, that would give us a sense if the sediments are potentially releasing any drivers of eutrophication into the bottom waters of the lake. So that concludes the description of the water quality tab and the measurements taken at the deep hole or index site in the lake. Now we'll move on to the next tab in the interactive report that is called Habitat. Here you'll see another aerial view of the lake and the watershed. In the upper right-hand corner of the map, you'll see a set of boxes for different physical habitat parameters you can toggle on and off. Here we see that the PHAB station tab is selected. PHAB stands for physical habitat, and since that tab is checked, we see the locations of the 10 randomly selected sites named A through J denoted on the map in yellow. These physical habitat observation methods are described in the US EPA's Survey of the Nation's Lakes Field Operations Manual and the Vermont Watershed Management Division's Field Methods Manual. If we check the big trees box, we see which of the 10 sites around the lake had larger proportions of their canopy along the shore made up of trees with trunks with a diameter at breast height larger than 0.3 meters. Not surprisingly, on Willoughby, we see the shore that is conserved as part of Willoughby State Forest has a higher proportion of large trees dominating the canopy along the shore, with the size of the green circles at sites E, D, and C being the largest. Now, if we move down and we check the small trees box and turn off the big trees box, we see what proportion of shoreline canopy is comprised of tall trees with narrow trunks that have a diameter at breast height under 0.3 meters. Intact tree canopy along shorelines and tributaries draining into lakes play an important role in dampening the energy from rainfall and heavy rains in particular. They serve as the first line of defense, intercepting the rain and slowing its descent down so that when it hits understory vegetation, shrubs, and finally hits the spongy duff layer of the forest floor, the rain droplet is more likely to be absorbed into the duff and ground rather than run off into the lake, taking with it soil and other pollutants. Next, we can click on the woody understory box, and this gives us the percent cover of the woody shrubs, saplings, and trees that are between 0.5 meters and 5 meters tall in what this diagram denotes as the sub-canopy layer and shrub layer. We see that about half of the sites have little to no woody understory, either from so much shading from the dense canopy or because the shoreline has been cleared for development. Moving down, we can check the floating plants box. Now you see little dots show up just at sites G and I. The very low nutrient levels in Lake Willoughby limit the amount of aquatic plant growth in a lake. This sparse growth is typical of an oligotrophic lake. Similarly, we only see any evidence of emergent plants at sites G and I. And we only see any evidence of submersed plants at sites G and I as well. In some lakes, you'll see differences between developed sites and undeveloped sites in the percent cover of floating, emergent, and submersed plants, with the percent covers at the undeveloped sites being what you would expect to see. We may see heavier growth off of developed sites since the plants often get more light because there is less shading from tree cover, and they get more nutrients running off of lawns, driveways, and impervious surfaces. But if the plant growth grows to nuisance levels and lakeshore owners go in and pull the plants, you can then see less plant cover at developed sites than undeveloped sites around the lake. If we look at shading around the lake, 7 of the 10 sites had lots of shading. Shading is measured using a densiometer 1 meter out from the waterline. There are 17 intercepts on a convex mirror, and the more intercepts that are shaded by leaves, the higher the shading rating. If we click on the embeddedness box, we see that sites J and B had embedded sediments, suggesting those sites may have more runoff of sediment entering the lake and warrant a closer look for mitigation options. So that completes our tour of the habitat boxes you can check on the map. Now we are going to turn our attention to the physical habitat summary metrics that were developed by the U.S. Environmental Protection Agency as part of the National Lakes Assessment. In each of the bars on the right, you see red, which denotes poor condition, yellow, which denotes fair condition, and blue, which denotes good condition. You'll notice that the width of each color is different for each metric. That's because the thresholds were set at different breakpoints for each metric, and the thresholds used in Vermont are from the Northern Appalachian ecoregion. The range or width of the red, poor, and blue, good rankings equates to the range found in Vermont. At the national or ecoregional scale, there may be lakes in even poorer condition or lakes in even better condition than we found in Vermont, but these bar graphs show the ranges found in Vermont. So we see that for the first metric, lakeshore disturbance in Willoughby, scores about midway in the fair condition range for the ecoregion. The Lakeshore Disturbance Index is based on field observations tallying the presence and proximity of 12 types of human activities or disturbances at the 10 shoreline positions A through J. Lakeshore disturbance incorporates both the extent of human activities and the intensity of those activities. The extent was expressed simply as the proportion of the shoreline stations that have at least one type of human activity recorded within their 15 by 15 meter shore plot and adjacent 10 by 15 meter littoral plot. The intensity of human disturbances was expressed by the mean proximity weighted tally of the number of types of human land use activities per observation station, where disturbances observed outside of the plots were given half the weight of those within the shoreline littoral plots. Next, we'll look at the Lakeshore Habitat Index. The Lakeshore Habitat Index is based on visual estimates of vegetation cover and structure in 3 vertical vegetation layers at 10, 15 meter by 15 meter plots adjacent to the lakeshore around the lake. Field data used to calculate indices of lakeshore habitat cover and complexity included cover class estimates of the canopy made up of large diameter and small diameter trees greater than 5 meters tall. Then it had percent cover of woody and non-woody vegetation in the mid-layer or sub-canopy and shrub layer from 5 meters tall to half a meter tall. And finally, estimates of the percent cover in the ground layer, which was any vegetation under a half meter, was used. We see that Lake Willoughby scores good for lakeshore habitat, but it is closer to the fair range, meaning that there were lakes at the state level that scored much better than Lake Willoughby did. The next habitat metric is for shallow water habitat. This index used observations from the 15 meter by 10 meter plot in the littoral zone or in-lake part of the 10 physical habitat site plots. It includes percent cover estimates of large woody snags greater than 0.3 meters in diameter, smaller diameter wood and brush that is 0.3 meters or less in diameter, inundated aquatic and herbaceous vegetation, and overhanging vegetation. We see here that Lake Willoughby scores good for the shallow water habitat index, although there are some lakes in the state that scored even better in the good category to the right of where the Willoughby dot falls. The final habitat metric from EPA's National Lake Assessment is the Physical Habitat Complexity Index, which is simply the arithmetic mean of the lakeshore habitat and shallow water habitat indices. We see that Willoughby scores good for this category as well. So next, within the Habitat tab, we can move to the Habitat Comparisons tab in the upper right hand of the page. Here we'll see how Lake Willoughby compares in 4 key parameters measured as part of a littoral habitat study conducted on Vermont inland lakes and reported on in the Examining Shorelines Littorally article in the North American Lake Management Society's Lakeline magazine, and in the report entitled Determining if Maine's Mandatory Shoreland Zoning Act Standards are Effective at Protecting Aquatic Habitat, shown in the bottom right of this slide. Lake Willoughby is denoted in the green is denoted in green in the graph. For comparison, the statewide mean and standard error for undeveloped lakeshore sites is shown in blue, and developed lakeshore sites is shown in red. The blue represents more natural conditions, and the red represents more disturbed conditions. We see that for embeddedness, Willoughby's sediments at the 10 PHAB sites was much less than both the undeveloped average and the developed average. Since Willoughby scored good for physical habitat complexity, shallow water habitat, and lakeshore habitat, it makes sense that the sediments were not embedded. While illegal, there are some landowners around lakes that import sand and put it on their shores, allowing it to wash into the lake. Hence, part of the reason developed sites had more sand than natural sites, although naturally sandy sites are also preferred when developing lakeshore. Since Willoughby has extensive natural sandy bottom areas, it is likely due to that natural condition that has a higher average cover of sand than the undeveloped sites. The percent cover of shade and trees is somewhere between the undeveloped sites and developed sites, which also agrees with the good rating that Willoughby had for the lakeshore habitat metric. So that concludes the habitat section of the report. Now we can move on to the inlet section. Here we see the watershed and all the mapped inlets that exist around the lake. Each is numbered. Once in a while, we'll encounter an inlet that isn't mapped or not be able to find an inlet that is mapped when we are sampling. Each inlet is numbered and similar to the habitat map. There are boxes you can click on and off. So if we click on the first box called sediment depth and the tab called physical and macrophytes, we see some dots appear at where the inlets meet the lake. If a delta was observed, then a rod is driven into the delta to see how far it goes in and how thick the sediment is. We adapted this approach from the Operation Healthy Lake study that was done on Lake Memphremagog. The thicker the sediment delta, the more likely there is a source of sediment upstream that might need to be addressed. Here we see that inlets 4 and 5 had the thickest or deepest sediment deltas, suggesting a look upstream at those streams for eroding road crossings or eroding banks might be in order. Next, we can click on the sediment delta box, which is the area of the sediment delta observed as measured in meters squared. Inlet 5 has a rather large delta. In fact, I believe it is one of the 2 largest deltas we have measured on our inland lakes to date. The other one is on Lake Carmi. But really, anywhere there is some measurable delta, it's worth looking upstream for sources of possible erosion. It could be historic loading, but if it's current, there may be ways to work to abate that erosion and prevent more sediment from entering the lake, which brings with it nutrients and other pollutants as well. Next, we can click on the algae percent cover box. Algae at the mouth of an inlet can be an indicator that nutrients like phosphorus may be entering the lake via that stream, as algae thrive when they have plenty of light and nutrients. In the upper left-hand corner, there is an example of an inlet with 90% cover of algae from an inlet draining into Shadow Lake in Glover, Vermont, suggesting that somewhere upstream of that inlet, there is likely a significant source of phosphorus that could use abating. But when we look at Lake Willoughby, only about 6 of the inlets have any algae present, and most have only 5 to 10% cover. Inlet 2 has 30% cover, and looking upstream for potential sources of phosphorus runoff at those 6 streams may be worthwhile to see what might be responsible for feeding the algae. Next, we can select aquatic plants percent cover, and on Willoughby, we had 0% cover at every inlet. In some lakes, aquatic plant cover can be rather abundant at the mouth of inlets, and the species of aquatic plants can tell you something about the likely nutrient conditions. For instance, when I see Elodea canadensis growing in abundance at an inlet mouth, I consider that an indication that there may be some nutrient sources upstream because Elodea does well in more nutrient-rich conditions. Next, we'll move to the Water Quality tab for the inlets, and we'll click on the Total Phosphorus box. Here we see some variability in the concentrations of total phosphorus depending on the inlet. Inlet 17 stands out as having the largest circle, and it had a rather high concentration of 108 micrograms per liter. Inlet 4, one of the inlets you'll recall that had a notable delta, has the next highest total phosphorus concentration, followed by Inlet 15. These results can help local groups prioritize which inlets might be worth monitoring more regularly through the La Rosa Partnership Program. Next, we can look at conductivity. The thing to do here is to look back in the Water Quality tab at the index site profile results from the open water site and see what the conductivity was running there. It was around 95 microsiemens per centimeter for the surface all the way to the bottom at 90 meters or so. Now, if we look at the table of conductivities measured at the inlets, we see they range in concentration from a low of 63 at Inlet 13 and a high of 493 at Inlet 9 at the south end of the lake. With the open water concentration running around 95, any of the inlets with concentrations much higher than that suggest there may be sources of pollution upstream worth looking into. One thing to keep in mind that just because the concentrations are high at one inlet as compared to another, if the inlet with the high concentration isn't very big, another much larger inlet with lower concentrations might be contributing a net higher amount of nutrients to a lake. That's why more regular monitoring, especially during high flows and low flows, is important to conduct to have a better understanding of which tributaries are the biggest contributors of nutrients to a lake. Inlet 9, for instance, is relatively small in comparison to Inlet 4 or 5. Now we can look at total chloride, which is a measure of road salt's impact to the lake. The detection limit for total chloride is 2 milligrams per liter, and that is what we see on our remote undeveloped lakes that have no road salt additions in their watersheds at all. A number of the inlets around the lake, Lake Willoughby, show concentrations of 2 milligrams per liter, which suggests those streams are not impacted by road salt. However, we have a few streams with higher than expected chloride levels, and stream number 9 has really high total chloride. Paved Route 5A crosses this stream at a point that is at the end of a hill, so it is likely that runoff from the road is entering the lake via this stream, and work should be done to abate that, which I believe is part of the project underway by Forest Parks and Recreation at the south end of the lake. The final water quality parameter in the inlet report view is turbidity, which is a measure of the suspended material in the water column. This parameter has been phased out as the meter was costly to maintain and buy calibrants for, and we have since replaced that sensor with one that measures phycocyanin, a pigment produced by cyanobacteria. However, for the lakes where we have turbidity readings, this can be an indicator of sediment runoff upstream. Here we see that only inlet 17 shows any evidence of turbidity. The final tab in the inlets view is for the outlet. In this view, you can see basic information about the outlet. Natural with artificial control means that Willoughby is a natural lake that has had a structure built at its outlet. Typically, the structures were added to elevate or attempt to stabilize or control the water level of the lake. Oftentimes, they were built for uses no longer employed or for power generation. A natural lake with no control structure at the outlet would be defined as natural, and a reservoir created from the damming of a stream or wetland complex would be denoted as artificial. That concludes the inlet tab features, and now let's move on to the protection classification tab. In the 1990s, Vermont received a grant from the US EPA to develop a lake protection classification system, which identified unique classes of lakes in the state. Unique lakes include types of lakes or lakes with natural features which are of limited number in the state. These lakes were considered a priority for protection due to their intrinsic value, having either a wilderness or wilderness-like character, being ultra-oligotrophic, of which sadly none are left in the state, having a feature whose scenic quality contributes significantly to a lake experience, or providing habitat for rare plant or animal species. Lakes may be ranking in more than one of the feature categories, but may not be both wilderness or wilderness-like. Willoughby is neither wilderness or wilderness-like, but it does score a high number for the total number of unique features, including natural beach, ledges, bouldered shore, steep slopes, peaks, and cliffs. I mentioned that Willoughby was not considered a wilderness lake, and here is sort of the rating system that's used to determine that. The description is a wilderness lake is remote, effort is required to reach it, the only visible evidence of human presence is non-permanent or temporary use, unobstructed obtrusive structures or features such as campsites, shelters or cabins, foot trails or four-wheel drive road, audible human activities only occasional, for example, trains or logging trucks, but not constant, like interstate or main thoroughfares. It is a natural body of water, and the distance to a two-wheel drive road is at least a third of a mile. And these are the evaluation criteria used. So wilderness lakes are an automatic priority for protection due to their limited number in Vermont and the likelihood that the loss of their wilderness status would be permanent. They are ranked for protection priority based on the level of present or past human influence. And so the highest rating you can get would be 10, and there's no visible past or present evidence of humans except for undeveloped campsites or foot trail. Rating of 9 would be may have some evidence of past or non-permanent human presence, so an example, old foundations, developed campsites, or may have four-wheel drive access, or both. And then a ranking of 8 would be unobtrusive structures on or near the shore that do not detract from wilderness character of a lake. So examples would be natural colored wooden shelter or temporary use cabin, dock, tent, platform. And they may have four-wheel drive access. Otherwise, it's not a wilderness lake. Wilderness Lake, on the other hand, has a wilderness character, but has a two-wheel drive road within a third of a mile of the lake, which may provide access to the lake, or has seasonal or year-round use structures, or has both of these characteristics. The maximum number of structures is an average of 1 per 1/3 of a mile of shoreline, and the audible human activity is harmonious with the wilderness lake character of the lake. So there are no loud motors or traffic noises. And the lake may have a natural outlet or an unobtrusive artificial outlet structure. And so you can see, I won't read it out here, but the different ratings are 10, 9, and 8 for wilderness lakes as well. Now, finally, the protection classification features unusual scenic or natural features categories includes beaches, ledges, bouldered shores, vegetation, islands, steep slopes, peaks, scenic lake bottoms, and cliffs. And these are the ranking criteria for that. So there may be more than one extremely rare feature, then it would get a 10 rating. As one extremely rare feature, it would get a 9 rating. More than one very rare feature, it would have an 8 rating, and one very rare feature would have a 7 rating. This is all using the lake protection classification system, and right here you would have just the total number of features that you're going to see in the next generation lake assessment report. So the final tab in the interactive report is the data tab. And this is where you can pull data from it or view it directly. So here, for example, the first tab in the data sub-tab is chemistry. And so here you can see all the chemistry that was data that was collected. You can export this to a CSV file, an Excel file, or print it just as you see it. And then the next tab would allow you to view and download any of the lakeshore and littoral habitat data. And then finally is the inlet habitat data. So here you can download any of the habitat data from the inlets as well. That concludes the tour of the next generation Lake Assessment Interactive Report. I hope you found this information useful and are be able to use it to help steward your lake better. If you're interested in going the next step, you could check out the lake land cover maps. We have those for all of the lakes 10 acres or greater, and you can find those on our website. And for each lake, it summarizes the land use, land cover for the 100-foot immediate riparian buffer around the entire lake and all the tributaries that are draining in it. And then you can sort of get a sense of what percentage of that area, those riparian buffers, is impervious or agriculture. You can look at the 250-foot buffer around the entire lake and get a summary of the land cover for that. And for Willoughby, you can see what percentage is impervious surfaces, roads, and agriculture. And then you can look at just the tributaries and see what the 100-foot buffer around those tributaries is dominated by for land cover. And you can look at the 100-foot buffer around the lakeshore to see what's the dominant stressors that might be impacting the lake and how you might, if your lake has a fair amount of impervious surfaces within 100 foot, you may want to investigate the LakeWise program, which helps folks restore their shorelines and be more lake friendly. And finally, you can see the summary of the watershed land use, land cover, and just sort of a sum total of all of the types of development pressures and land cover sort of stresses that may be impacting your lake. Thank you for your attention. Here's my contact information, and I appreciate your interest in helping to steward Vermont's lakes.